Okay, now I've got to move Jesus again. He's in the way again. All right, there we go. So, sorry about that. Let's imagine for a moment we have in front of us a first order differential equation, and we can neither find the solution nor invent a method for solving it analytically. This is not as bad a predicament as one might think, since the differential equation itself can be the fount of information about how its solutions behave. Okay? We begin our study of first order differential equations with two ways of analyzing a differential equation qualitatively. Both of these enable us to determine in an approximate sense what a solution curve must look like without actually solving the equation. So that's why they call it solution curves without a solution. The first of these is what they call direction fields. Now, if indeed your dy dx is some function of x and y, like this, okay? Now, time out a moment here. We saw back in section 1.2 that whenever you have a f of xy, like this right here, and the partial of f with respect to y satisfies certain continuity conditions, qualitative questions about the existence and uniqueness can be answered. Remember, we talked about that, and that's what it's called, uniqueness and existence and uniqueness. In this section, we'll see how the other qualitative questions about the properties of solutions, for instance, how does a solution behave near a certain point? How does a solution behave as x is going to infinity? Can often be answered when the function f depends solely on the variable y. Okay? So we begin with a simple concept from calculus. Here it is. Dy dx, that derivative of a differentiable function y is equal to some function of x, it gives the slope of the tangent line at points on the graph. So, if you know that y is equal to y of x, then a first order differential equation dy dx equal to f of xy is necessarily just a differential function on its interval of definition. It must also be continuous on that interval of definition. Thus, the corresponding solution curve on that interval must have no breaks and must possess a tangent line at every point. So you can't have any cusps or corners or things like this. You have to have basically a nice, smooth, continuous function. If you have it, you can go with it. The function f is then the in the normal form is called, okay, if you remember the normal form when we wrote the biggest derivative out here and every other derivative here. And since we're dealing with first order derivatives, the biggest derivative is dy dx, and here you don't have any derivatives, but you do have your x and your y. Okay, so let's just suppose we know those. That function is measurable. Okay, now, so what we do know is at any point xy, you can plug it into this function value, get an answer. You know that's the slope at that point. Positive slope, steep slope, zero slope, negative slope, whatever. You know it. That will be f of xy will be your slope at that point. Okay? And we can picture that as at every point you have a little lineal element that basically points to you which way it's going. So here's one, dy dx. We looked at this as one of the earliest ones we had. Dy dx is equal to 0.2 xy. Okay? Now, this f of xy up here is now this 0.2 xy. Now, if you pick a point like the point 2,3, and that is on this curve, and it looks like that would be perfectly legitimate for it to be on the curve, there it is, So put 2 in for x, 3 in for y, and you have 0.2 times 2 is 0.4 times 3 would be 1.2. That's going to be the slope at that point. The slope 1.2 at that point. So if you draw your slope in here, it's just a little bit more than a one-to-one slope, so it's up, going up like that. You know that's the direction of your solution curve at that point. Okay, at the point. Pick another point and you'll get a direction there and here and there. Every point you pick, you can come up with a direction vector. In other words, where the function would be heading if it's at that value. Okay? We call the collection of those, excuse me, sorry. My head is clogging up and my throat is going dry. Hold on just a second. Okay. So this is what we call a direction field. If we systematically evaluate F over a rectangular grid of points in the xy plane and draw a line element, just a little pointer, you know, saying which direction it's going, at each point xy of the grid with the slope f of xy. Plug in the xy point and you get the slope. Then the collection of these elements is called the direction field, sometimes also called the slope field of that differential equation, dy dx is equal to f of xy. Visually, the direction field suggests the appearance or shape of a family of solutions of the differential equation, and consequently, it may be possible to see at a glance certain qualitative aspects of the solution. In other words, regions of space in which the solution exhibits an unusual behavior or something like that. A single solution curve that passes through a direction field must follow the flow pattern of the field. It is tangent to the linear element when it intersects the point on the graph. So here dy dx is equal to sine of x plus y. And we want to do that over a region of space. Notice that 3 solution curves shown in the color in the direction field. So let's start with a point. Now they don't give us values, so to speak, I don't think. But let's just say x is equal to 0 here and y is equal to, you know, some value. We don't know what it is, okay? Then the sine of y is going to be the direction here. And you see, once it gets going, you can follow the arrows and they tend to go back down again, the best curve that you can. This one starts off going down, then turns and heads back up, and then turns and heads back down. Okay? This one starts going down, 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 and finally turns and starts going up again. Okay? Now, all depends on where your initial value is. Okay? That would determine a lot about your direction field. Okay. So let's see if we can do example 1. Now the problem is we have a lot of points on a graph, and you almost seems like you need to do an arrow for each one. They've done it for you here, computer driven, computer drawn, pretty nice. Okay, thank you very much. If you're doing these by hand, it's a real pain in the neck. Okay, so here's our differential equation. Dy dx is equal to 0.2 times x times y. Now, one thing to note right off the top, when x is equal to 0, that's anywhere on the y-axis. Anywhere on the y-axis, that slope is 0, meaning it's a horizontal slope. And sure enough, all these little arrows have a 0 slope. Yeah. Now, sorry, I'm having trouble breathing. Anywhere where y is equal to 0, you also have that. It's anywhere on the x-axis. There your slopes are 0. Now, anywhere slightly up from that, you will then have gradually increasing slopes. In some places, decreasing in other places. All you have to do is plug in a value. Let's take 2, 2, right there. So that would be 0.2 times 4, which is 0.8. The slope here is 0.8, just a little bit less than a 45. Okay? I can't get too far out because this is restricted to -4 to 4, both x and y. But you can plug in any of those values here. -4 minus 4 should give you that one. Let's see what that would be. 0.2 times 16. 3.2, I think it is. Goodness, my brain's not working. And you see here, there's a pretty steep slope there. Slope of 3.2. So you see, any value you put in there will give you any xy point right over here. How about 4, -2? Let's put that in. 4 times -2 is -8 times 1.2 is -1.6, and sure enough, that looks like it's going downhill. Not quite at 1.5, but fairly close. Okay, that's how you get your direction fields. Now, as I said, it's going to take a lot of calculations to fill up just a little -4 to +4, -4 to +4, x and y. That's a lot of points to put in. Every one of those coordinate grid points. Now, in section 1.1, we saw that if you had this equation, y is equal to e to the 0.1 x squared. That's an explicit solution of a differential equation that we're just looking at. Dy dx is equal to 0.2 times xy. Now, we did that earlier, okay? You should verify that a one-parameter family of solutions of the same equation is given by this. So in other words, just put a constant variable on it and you'll that gives you your parametric dependency, you might say. Okay, so the purposes of this comparison, and here are those solution curves here. When c is equal to 0, you're on the y-axis, because when c is equal to 0, hold on just a second. I think I must have eaten my lunch a little too fast and without drinking enough, because I'm dry as a bone right now. So this line here is where c is equal to 0, right here. So you have y is equal to 0. Well, there it is. See this line here? All those direction arrows are pointing horizontally. So there is the place where that is indeed true. Now, when your c is something positive, then you're following these curves up here. When c is negative, you're following the ones down here. These are the actual curves for various choices of c, positive c's and negative c's. These are your direction fields, and sure enough, these duplicate these pretty closely. Okay, so that's just one example. Let's do example 2. If I could find my cursor, there it is. It disappears so fast. So let's do example 2. Use a direction field to sketch an approximate solution curve for the initial value problem. dy dx is equal to sine y. Okay? And y of 0, here's your initial value, initial condition. Y of 0 is equal to minus 3/2. Okay? All right. So this is your x value. This is your y value. So dy dx is equal to sine y. Well, that's sine of minus 3/2. Now, again, just about any time in calculus, and certainly in differential equation, when we're dealing with trig functions, you're dealing with radians. Unless you see that little degree symbol, you're dealing with radians. So let's just see what that initial slope is. Now, by the way, they did a couple of things first. They said, before proceeding, recall from the continuity, f is equal to sine y. That's continuous everywhere. And the partial of f with respect to y. This is a partial differential equation. It kind of is, but we're not solving that. We're just taking the partial. Well, I know many of you haven't had that yet. If you take the partial of f, this is your f, sine y, right here. Partial of f with respect to y would be, derivative of sine would be cosine. And that's what they did here. Partial of f with respect to y is cosine y. And that's continuous everywhere. So now we know we have a unique, the solution does exist and it is unique. That's all that was doing. Now we set our computer software for a 5x5 rectangular region, which we had the computer software, where specify that because of initial condition, points in that region with vertical and horizontal separation, they say of about 1/2 unit. Wow. Thank goodness they're using a computer. There would be an awful lot of calculations made. That is, at points MH and NH, where H is equal to 1/2, yeah. M and N are integers, and you're splitting M into minus 10 to plus 10, N from minus 10 to plus 10. Now, because the right-hand side of this is sine y, okay, it's 0 at y is equal to 0. Okay, now we haven't got the figure of that yet, but we know it's 0 anytime y is 0. I swear my thing keeps falling off my pocket. As soon as I put it back on, then the cord falls, and then that drags it off my pocket again. So it's sort of a never-ending cycle here. Okay. At any value y, your slope is 0. So every value where y is 0, your slope is 0. So anywhere on the x-axis. That would be just about like we saw here. Now, the rest of it's not going to work this way, but that would be, this line right here would be identical on this problem. Because when y is 0, which is neither positive or negative, 0, then this slope is always 0. Okay. Now, we have when x is equal to 0, your y is equal to minus 3 halves. So x equals 0 would be here, minus 3 halves would be somewhere here. Now, of course, this is not the same slide, okay? So we do have an initial value. Your slope here is minus 3 halves, so it's going downward pretty steeply at minus 1.5, okay? Obviously, this is not that direction field, but just pointing out where it would be if you had that same grid, okay? So they're doing from minus 10 to 10 for x and n. All right, so let's go down to figure 1.4. Okay, here we have it. These can get to be a little tedious at times, but here's what we see. Now, we said before, when anytime y is equal to 0, because sine of y is going to be 0, so all these are horizontal here, okay? But we started with x was 0, y is negative 3 halves, right? Yeah, 0, negative 3 halves. That was our initial point. So x0 is here, 3 halves is 1.5 here, there it is. And the slope there is indeed, that's why I had my calculator in my hand, the y is minus 3 halves. And remember, you're in radian mode. So let me turn on my calculator. Excuse me just a minute. I think I know one reason I'm clogging up some. Earlier this morning, it was quite not cold, but it was cool enough, and I had to turn off the ceiling fan. I just remembered we were sitting in here all cooped up and ceiling fan. Okay, let me get my calculator. Because I'm going to be using sines, I turn it sideways. Now, at this point, 0 minus 3 halves, remember your function is f of x is equal to sine y. F of xy is equal to sine y. So the x really doesn't matter here, it's the sine. So remember, you're in radian mode. Make sure your calculator, I'm on my phone, it's in radian mode. You see the RAD up there. If you want to change it, the DEG down here, you press that and then that goes. In fact, I think that disappears. If you don't see anything, it's in degrees. You have to see radian for it to be in radian mode. So let's do 3 halves, that's 1.5. 1.5, negate that, and then let's take a sine of it. And that's almost a -1 slope. Awfully close to a -1 slope. And sure enough here, that's what it appears. Right there at, see, this is -2. -1 would be right here. -1.5 would be right there. And the slope there is -3 halves. Now, here's the good news. Once you know the slope one place, you know it all along there, because all your y's are the same here at -1.5. So every one of those places, the slope is almost -1. Okay? Now, so point almost -1 in this way, and then go over here to y is equal to -2. But now your x is whatever value that is. But guess what? All you need to know for the next slope is plug in sine of -2. So do 2, negate that, and do the sine, and you get 0.90. So it's not quite as steeply negative as before, but still awfully close to -1. We'll go down to minus 2. And all along there, the entire thing here, this is going to be a negative 0.9 slope. Then do the next one, 2.5, 2.5, negate that, and do a sine of that. And now you're just over a little more negative than negative 1/2, negative 0.59, negative 0.6 basically. And this one here, 2.5, this would be about a little bit more, a little bit steeper than 1/2. Okay. Well, let's go to the next one. 3, negative 3, sine of that is going to be negative 0.1. So this is very shallow slope here. At negative 3, it's a pretty shallow slope here. And at some point down there, in fact, I'll tell you exactly what point. When y is equal to negative 3.14, because guess what? That's pi. So if you got a negative pi, I'm going to press the pi key. Okay, I'm going to negate that, and you take the sine of that, and of course you know that is 0. So down here at some point 3.14, negative 3.14, all your slopes are 0 again. Okay, now you go a little beyond that and the slopes are slightly positive now, and beyond that it's a little more positive and more positive and more positive until ultimately you get to that. Now we're going to run out of room. I don't think anyone else came in here. No. Okay. Now, so when y is equal to 0, your slope is 0. When y is equal to negative pi, your slope is 0. When y is equal to plus pi, your slope is 0. Okay? So somewhere in between this one and that one is 0. And in between there, they're all moving in the same direction. They start off slow and then increase until they get to a slope of -1. Then they start decreasing again and going to 0. Up here, they would start close to 0 and then start moving up ever so slightly, and ultimately at some point here, at some point here, they would approach 0. So they start going up gradually, going up almost at a slope of 1, then start declining in the slope until they're back here again. So you have a curve that looks just like this one, only it's a mirror image of it across the board here. And here's one coming down here that mimics this one. The one down here mimics that one. So you have your periodic distribution in y. Okay, so that's one way of looking at direction fields. Plot the easy stuff, and once you get the easy stuff plotted, you get a general idea of where you're going there. Now, I think I did that. I don't think anyone else is coming in. Let me just check to make sure. Nope, we're all still here. Actually, we lost one person. Looks like we lost who is it we lost? Oh, Jemanuel. Okay, we lost Jemanuel. Okay, I don't know if he's coming back or not. So, here are the remarks here. This was a fairly short section here. It's not all of one section. It's 2.1.1. Sketching a direction field by hand is straightforward, but major time consuming. Okay, probably one of those tasks about which an argument can be made for doing it once or twice in a lifetime. That's sort of an exaggeration, but it is overall most efficiently carried out by means of computer software, blah blah blah. Before calculators and PCs and software, the method of isoclines was used to facilitate sketching a direction field by hand. Is it time? You're right. Okay. Well, we just did finish 2.1. That's all we're going to say. And isocline, by the way, the prefix iso means same, cline means elevation. So if you've ever seen a topographic map, those little curves that go throughout the map, those are isoclines, and that's the method they kind of use here. So we did finish 2.1. Next, 2.1.1. Next time we will go with 2.1.2 on page 39. Okay. We'll talk about the other kind of form. These were direction fields. Homework exercises here. If you could turn over to page 44, under direction fields, you can do 1 or 3. Any of the odds 5 through 11. If those are in the back of the book, you can do them. And 13. No, okay, 13 and 15. Okay, so stop there. The discussion problem, probably the answers aren't in the back of the book, and there's only one odd one there anyway. So those are the ones we do for this time. Okay, next time we'll pick up with 2.1.2 on page 39. Any questions? Okay. If not, I'm going to stop sharing. I'm sick and tired of sharing now. Okay, sorry that the Zoom wouldn't log in today. We lost a lot of time, but we did make some progress. So if there are no questions, I'm going to go on and end the meeting. And even though it's the first time we've met all week, I say again, like I did last Wednesday, have a good weekend. But this time you don't have a holiday weekend, just a regular weekend. So we'll see you Monday. See some of you tomorrow in linear algebra. Okay? Any questions? Take care. See you either tomorrow or Monday, or both. Yeah, what's your question? Okay, you mean not, okay, if they return to campus sometime this semester, fall semester? Okay, I'll preface this with one thing. I doubt if it's going to happen. Okay, I'll say that. Now, have you heard anything that indicates they might be thinking that way? Okay. As far as I know, the college is probably going to stay remote. Even if they don't, I think I can answer honestly here. I don't think this class will go back on campus, and the reason is my health. Okay, because I have a mild case of leukemia. I have to take chemo, not often, but I'll probably have to take at least one round this term, and that does this to my immune system. So I don't believe they either want me on campus or would even allow me on campus. So this course, I think we can safely say we'll probably stay off campus. I can't say that for your other classes. Okay, if you have other classes, you'll have to just go with that. Here's the other reason I don't think it's going to happen. Now, I don't know this for a fact, but I know one of my math instructors, and remember, all the classes that are not career tech or nursing or some of those areas, all the academic classes are being offered virtually or online. All of them are remote, none of them. But yet they decided to make all instructors go to campus 2 days a week, either Monday, Wednesday, or Tuesday, Thursday, and teach their virtual classes from campus rather than from home. Well, 3 weeks in, which is just about the incubation period, one of my instructors, math instructors, got sick. Now, whether it's COVID or not, I don't know, but she was running a fever. They wouldn't allow her on campus. She taught remotely for ever since March, never got sick on campus, and within 3 weeks, she was sick. Now, I'm hoping it's not COVID, but the odds are it may be. And if it is, then they have to answer the question, what was the point? Why did they make an instructor risk her health by going back to campus and there she, I mean, who knows? This virus is mean and nasty. It can have long-term effects. Okay, so I'm going to be screaming bloody murder if they start saying people need to go back to campus. Okay, of course they'll let me scream all I want to, but they'll do whatever they want to. But I would say the odds are very slim that we're going back to campus. This class, almost nil that we're going back. Okay, I'm not sure that answers your question, but that's my best guess at it. Okay, all righty. Any others? Okay, well then I'll end the meeting for everybody. Take care, be safe, take care of yourself, have a good weekend. See you Monday or tomorrow for some of you. Bye-bye.